Hello everybody, welcome to the first video of mine on a pure paper for A Level. So I'm starting this time with paper 2, weirdly, because paper 2 is actually what my students are studying on right now in terms of paper that's been taken home. I will eventually have all papers done, is my wish. In the corner, if you're wondering, this is Euclid and this is Euler. So two brilliant pure mathematicians. I could have used Newton again like I did for the mechanics video, but Newton, the mechanics side is almost all Newtonian mechanics. So Newton's celebrated enough. I thought I'd put Euclid in, a bit of trivium, some Greek stuff, and Euler, one of the best ever. Anyway, that's explaining the illustrations. Now let's explain the maths. Let's get to it. Let's have a look together at question 1. So we're told we have this relation in between x and y. So we're told that 2 to the power x multiplied by 4 to the power y is 1 over 2 root 2. Our task is to express y as a function of x. So essentially we want this in the form y equals. So y must be the subject, all in terms of x. The key thing here is to note that all of this is in terms of powers of 2. So let's rewrite it explicitly in powers of 2. We've got 2 to the power x, 4 is 2 squared. So I'm going to rewrite this as 2 squared y. And then 2 root 2, 1 over 2 root 2. Let's just think about if we can neaten this up straight away. Because it's 1 over, that's the same as 2 root 2 to the negative 1. 2 root 2 itself, though, is the same as 2 to the power 3 over 2. Because it's 2 to the 1 times 2 to the half. But because it's 1 over that, it's the same as that to the minus 1. So essentially, this is 2 to the power minus 3 over 2. We can simplify this by using the laws of powers. So this becomes 2 to the power x times 2 to the power 2y equals 2 to the power negative 3 over 2. We can combine this again using the laws of powers into 2 to the power of x plus 2y equals 2 to the power minus 3 over 2. So now we have an equation. One side is equal to the other, obviously. Now the base values are the same. The base is both 2, one side is equal to the other. The only way this can be the case, therefore, is if the powers are also equal. So from this line, we can deduce that x plus 2y must equal minus 3 over 2. So we can then write this down as a more simple equation. So x plus 2y must equal minus 3 over 2. Just using that yellow. We can now rearrange that. So if I subtract x from both sides, 2y must be minus x minus 3 over 2. Therefore, dividing through everything by 2, we get y must be minus x over 2. And then half the minus 3 over 2, that goes to minus 3 over 4. That's our final answer where we have y as a function of x. Y equals minus x over 2 minus 3/4. Question 2 is about the speed of a small jet aircraft being measured every 5 seconds, starting from the time it turned onto a runway until the time when it left the ground. We've got these results here in a table below, and the time in seconds and the speed in meters per second. So using all this information, we need to estimate the length of a runway used by the jet to take off. This might not be immediately obvious what we need to do. What I'd suggest here, you've got a table of values. Time is the independent variable. Speed depends upon the time. So we could imagine this, I would suggest, as a graph of speed against time. So if we sketch it out, we'd get something that looks a little bit like this. So time is going up in even increments of every 5 seconds when it's being measured, and the speed is increasing. And the gaps between the measured speeds is increasing, which tells us that this is accelerating throughout. So for example, in the first 5 seconds, it only increases in speed by 3 meters per second, but between 5 and 10 seconds, it goes up by 5 meters per second. Each gap's getting bigger. Without saying it, really, this is a slightly, not awkward question, but it needs more thinking. This is essentially going to be an application of the trapezium rule. Because if we took the area underneath the graph of a speed time graph, that tells us the distance travelled, and that's going to relate to the length of a runway. So to find the length of a runway, what we need to do is use the trapezium rule, and it is in the formula book. We have this result here. So the length of a runway is going to be given by estimating the area underneath this curve. And to do that, we're going to use this trapezium rule. H is essentially just the width of each strip. So we're going to go for the first 25 seconds. So we've got 1, 2, 3, 4, 5 different intervals. 25 divided by 5 is 5. So here, we're just going to be using h is equal to 5. So it's just a case now of just carefully plugging in the numbers. So the length of a runway, we're going to use the trapezium rule to approximate. So it's going to be a half of h, so it's going to be a half times 5. y0 plus yn. So y0 is like the first height, yn is the last height. So y0 is going to be 2, and yn, the last one, is going to be the last speed measured, which is 42. So it's 2 plus 42, plus 2 lots of all the other ones added together. So it's going to be 2 lots of 5 plus 10 plus 18 plus 28. So if we just carefully do this on our calculators like so, we're going to get 1/2 times 5, open brackets, 2 add 42, then plus 2 lots of 5 add 10, add 18, add 28, close brackets, close final big brackets. We get 415. So that's going to be 415 meters. So that's our final answer for A, 415 meters. So I'll just underline that and put here that's our answer for part A. Part B, we need to explain whether the answer to part A is an underestimate or an overestimate of the length of the runway used by the jet to take off. So essentially what we need to consider here is these areas of these trapeziums we've worked out, would that give an over or underestimate for each one? Well, if I just, for example, consider this final trapezium, if I just sketch this here, you can hopefully see that this graph, because it's curving upwards, so that's a trapezium. If I imagine the graph here, it's sort of going faster, so it's like this each and every time. So the trapezium is actually going to include an extra piece here, which actually isn't underneath the curve. That's to say each trapezium is going to slightly overestimate the actual distance travelled in each 5-second interval, because the curve is actually convex. And so that's the main reason. So for an explanation for part B, something like this would suffice. Something to say part A is going to be an overestimate, since the graph of speed versus time is convex. The acceleration is always increasing. So essentially what we're trying to say here, because it's accelerating each and every time, it won't quite take 415 meters to get up to a speed of 42 meters per second. It's a slight overestimate what we've done, based on this curve being convex if we were to draw it out. Question 3 is about a sector, AOB, of a circle, radius 5 centimeters, and angle AOB at the center is 40 degrees. So a student here is attempting to find the area of a sector, and their attempt is shown below. So the area of a sector is half r squared theta. That should be familiar to you, hopefully. So we've done a half multiplied by 5 squared multiplied by theta, which they said is 40 degrees. It all looks reasonable. If you try this on the calculator, you do get 500. However, the question here does say the student's made an error. What is the error made by the student? Well, essentially, what we need to remember is to find the area of the sector, or the length of an arc, using the formula half r squared theta. That will only work when we're measuring the angle in radians. So essentially, the error made by the student is simply that the student is using angle units of degrees. They need to be using radians. Part B, to write the correct solution, we just need to adapt this 40-degree angle here to get it in terms of radians. So what we need to remember, to change from degrees to radians, we just simply multiply by 2 pi and divide by 360. And so this angle here, the 40-degree angle, we need to convert it into 40 times 2 pi all over 360. And if we do that and use that in radians rather than in degrees, the answer will come out correct. Another way to remember it is there are 2 pi radians in a full circle. So the corrected solution will be something like this. The area is a half times 5 squared times 40 times 2 pi over 360. That converts the angle from degrees into radians. In exact form, you'd get 25 pi over 9, which is absolutely fine. Or if you want to give a decimal approximation, you should get 8.73 cm squared, correct to 3 significant figures. So the key thing here is to not be using degrees, but to convert from degrees to radians by multiplying by this conversion factor, times by 2 pi all over 360. Question 4 is about parametric equations. We've got a curve C1 defined parametrically as x being 10 cos t and y is 4 root 2 multiplied by sine t, where t is in between 0 inclusive and 2 pi exclusive. And it meets the circle C subscript 2 with equation x squared plus y squared equals 66 at 4 distinct points as shown. One of these points, though, is in the 4th quadrant, this one here, S. So find the Cartesian coordinates of S. So essentially we want our coordinates S in terms of an x coordinate and a y coordinate. So in other words, we don't want this to have anything to do with a parameter t. We want it all in terms of x's and y's. So what we could do is sub in x here into the equation of a circle and also y here into this equation. So the next step would be to say we've got x squared, which is 10 cos t all squared, plus y all squared, which is 4 root 2 sine t all squared. That's going to be equal to 66. So the first step, we're just going to sub in to the Cartesian C2 equation. Now we're going to have sine squareds and cos squareds, so we should be able to use the identity cos squared plus sine squared equals 1 in a moment. So expand this out, we're going to get 100 cos squared t. This one is going to get 16 times by 2, it's going to be 32 sine squared t, and then that equals 66. So what we need to do really is to get these all in terms of either a cos squared and a sine squared. You could go either way round. I'm just choosing to get it all in terms of cos squared. If you choose sine squared and follow it through correctly, you should still generate the correct solution. But anyway, I'm going to change the sine squareds in terms of cos squareds. So the next step, just leave the cos squareds as they are. So we've got 100 cos squared t plus 32. Now, to rearrange this in terms of cos squareds, that's going to become 1 minus cos squared t. And that's going to equal 66. So expand out, we get 100 cos squared t plus 32, then minus 32 cos squared t equals 66. So now, if I were to subtract 32 from both sides, and to simplify how many cos squareds I've got, 100 take away 32 of them gives 68. So I've got 68 cos squared t. Then 66 minus 32 gives 34. divide through by 68, so we get cos squared t equals 34 over 68, which of course is a half. Square root both sides now. We get cos t is going to be plus or minus a square root of a half. So if you square root a half, that's going to be root 2 over 2. So cos t is plus or minus root 2 over 2. And before going on, we may as well just have a look at this coordinate s here. So s, this coordinate, is clearly going to be where x is positive, and this is where y is negative. So it's just worth drawing our attention to this now. X is 10 cosine t. So if x is positive, then we need this x value, obviously, to be positive only. So we can only have cos t being positive itself. So what we can say here is, we can just say it's plus root 2 over 2 only. Then we can make a note if we want to, positive, since 10 cos t must be positive. So then we can find the principal value. So the principal value is that t equals cos minus 1 of root 2 over 2. And if you try that, you'll get a value of pi over 4. So that's the principal value. So if we just remind ourselves of a CAS diagram at this point, then if t is pi over 4, this would be obviously 45 degrees in terms of degrees. That's where both cosine and the adjacent, so cosine and sine would be both positive. But here, y is sine t. We need sine to be negative. So we're wanting a solution where cos is positive, but sine is negative. So what we're actually wanting here is that t is 7 pi over 4. So this principal value is actually no good. What we need is 7 pi over 4. So this one here we're going to reject. Rejecting it because we require sine to be negative. So then we can piece in, therefore, the coordinates of s. So therefore, s is going to be 10 cos 7 pi over 4 and 4 root 2 sine 7 pi over 4. And if you try that on the calculator or are comfortable with your exact values, I'd suggest use a calculator to be fair, just to show you here. So we've got 10 cos 7 pi over 4 for the x value. So x is just simply 5 root 2. Then if we try this for sine 7 pi over 4, we're going to get 4 root 2 sine 7 pi over 4. And that's going to give us a value of, should be negative. It is, we get minus 4. So that's the coordinates of s, which is what we were required to find. Therefore, we've done question 4. So onwards and upwards, let's have a look at the next one, question 5. Question 5 is, we've got a figure here, the equation y equals square root of x. Point P, x and y is defined on the curve here. And the rectangle, this very thin strip shown shaded, has height y and width delta x. So we need to calculate the limit as delta x shrinks towards 0 from x being 4 up to 9, the sum of all these y values, root x, multiplied by these tiny delta x's. So what this is saying here is, imagine the area as the width is becoming infinitesimally small, all these bars in between 4 and 9. Well, if all these bars of delta x width were put in between 4 and 9, and the widths were made smaller and smaller, this area would become the exact area underneath the curve. This is a standard result, and it's mentioned in the last chapter in the Year 2 Edexcel book on integration. The general result is as follows. Essentially, it's going to become the exact integral. So this here, where the function of x is particularly root x, we can take this, adapt, and say this is going to be one the same as the integral from x being from 4 up to 9 of root x dx. I'm just going to call root x x to the half, because in index form I believe things are easier to see to integrate. So root x, I'm just writing as x to the half. Therefore we know what to do. This is actually a very simple integral once we understand what concept we're being tested on. So of course the half will increase to 3 over 2, then we divide by that new power, which is the same as multiplying by 2/3. We get 2/3 x to the power 3 over 2 in between the limits of x being equal to 9, then subtract the limit when x is equal to 4. So we're going to get 2/3 times 9 to the 3 over 2, then we're going to minus off 2/3 times 4 to the power 3 over 2. So we can do this on the calculator, why not? So the first one, 2/3 multiplied by 9 to the power 3 over 2, I'm just going to put it as 1.5, it's the same thing, minus 2/3 multiplied by 4 to the power 3 over 2, which is the same as 1.5. We're going to get 38 over 3 as an exact fraction. So keep it in exact form because that tends to be the best way. So question 5 is the same as the integral of square root of x from 4 to 9, which gives 38 over 3. And that's question 5 complete. Question 6 relates to function notation. So we've got figure 4 here, this curve, and it's y equals g of x. And g of x is defined piecemeal, so it's defined in 2 parts. So for x being equal or less than 2, g of x is x minus 2 all squared plus 1, which is this curved part here. And when x is bigger than 2, g of x is defined as 4x minus 7. The crucial point when x is actually equal to 2 would generate a value of g of x equaling 1 for both parts. So that's why it looks almost continuous, although this here is actually a discontinuity. At any rate, our first question is to find the value of g of 0. So what we need to do for this one is, first of all, to work out g of 0 first. And consider this as g of whatever g of 0 is. So first of all, g of 0 is just what I get if I plug 0 into this function. 0 is 2 or less, so I'm going to plug it into this top one. So if x is 0, that'll give 0 minus 2 all squared plus 1, which is 5. So the next step, so g of 0, which we just worked out, of course, that's one of the same as saying I need to work out what g of 5 is, because g of 0 is 5. So now we just plug in 5 into this expression. So this time, when g is 5, x is bigger than 2, so we're looking at this expression at the bottom. So we're going to have 4 lots of 5 minus 7 using this one here, whereas before we used that one. And of course 4 times 5 is 20, and then if we were to do the 20 minus the 7, that would get us to a value of 13. So g of 5 is simply 13. We can now think about looking at part B and answering this one. So part B, we need to find all values of x for which g of x is greater than 28. So what I'm going to do here, I'm going to imagine a line where g of x is actually equal to 28. So I'm going to label this on as g of x equaling 28. So if I want g of x to be bigger than 28, then there's 2 separate parts I'm considering to this graph. So the first part I might be considering is this bit here. And the second part, where g of x is clearly going to be greater than 28, is going to be this part here. It's got two different bits, two different cases. So let's think first of all about case A. So I'm going to call this case A and then case B. Case A, of course, hopefully you can see, this is where we've clearly got x less than or equal to 2. Whereas case B is this second piece. This is defined when x is greater than 0. So first of all, let's just consider case A for a moment. So for case A, what we have here is, looking at this top one, we've got x minus 2 squared plus 1 must be bigger than 28. This can now be, of course, rearranged. So if I take 1 from both sides, I can see that x minus 2 all squared needs to be bigger than 27. Now if I consider square rooting both sides for a second, this side will become x minus 2, obviously. This side will become root 27. But what I want to do here is just to sketch this out for a moment. So if you imagine a graph of x minus 2 all squared, something like this, and then we want it to be at least at a height of 27. So just like we did here, imagine a horizontal line across at a height of 27. Then this point here is going to correspond where x minus 2 equals positive square root 27. And the lower one will be where x minus 2 equals the negative root of 27. Now, because we're looking at, for the case where x is actually less than 2, we're looking at this lower end one here. So actually what we're wanting is this result where x minus 2 is actually needs to be less than negative root 27, because we're after a solution on this side of it. We want the solution to be on the purple side, which I'm going to show you here. So just in this diagram here, we want our solution to be up here somewhere. So therefore what we're needing is x minus 2 to be less than minus root 27. So therefore for case A, let's move this up here. Therefore we need x to be less than, if we add 2 to both sides, 2 minus root 27. Now we'll think about case B, and we'll put these together at the end. So for case B, where x is clearly 2 or greater, we're just solving where 4x minus 7 is greater than 28. So 4x minus 7 greater than 28. Add 7 to both sides, gives 4x needs to be greater than 35. So therefore x must be greater than 35 over 4. So therefore the solution set is, therefore we need x to be, whoops, I'll change colour. X to be less than 2 minus root 27, or x such that x is greater than 35 over 4. Now part C, we want to find a function h, which is defined by h of x equals x minus 2 all squared plus 1, the same as what g of x is, but this time we're only defining it for x being 2 or less. So essentially, h of x is just for 2 or less, so it's going to be this part here. Now this curve, hopefully you can see, is a 1-to-1 mapping. Each one version of x goes to one version of y. Each 1x goes to 1y. For a function to have an inverse, it must be a one-to-one mapping. H of x defined this way is, but g of x, this one with part A and part B, isn't. This is a many-to-one mapping. For example, looking where g of x equals 28, x being a negative value and x being a positive value, both maps to that point. So to answer part C, we need to say something like this. Essentially, h is a one-to-one function, but g is not. And if you want to impress the examiner, you might want to say g is many to one. Finally, for part D, we need to solve this equation, h minus 1 of x. This means the inverse function equals minus 1/2. So what we need to do here, first of all, is just to rewrite h of x and get x to be the subject. So what I'm going to do here, h of x, I'm just going to call y for simplicity. So I'm going to get x as a subject instead of y. So let y, which is h of x, of course, equal x minus 2 all squared plus 1. Rearrange to make x the subject. So if I subtract 1 from both sides, I get y minus 1 equals x minus 2 all squared. Before I go on, actually, I'm just going to make a small point over here and go and explain why this is important to do now rather than later. It's just talking about the domain and range of the inverse function h minus 1. So for h minus 1, which is the inverse of h, let's think about what we know for h of x, first of all. The reason I'm doing this now is because when we square root this, we need to consider both the positive and negative square roots. But for h of x, the domain for h of x was x being less than or equal to 2. And the range for h of x is, of course, well, we can see here that h of x needs to be at least 1. It's got a minimum point when x is 2, and when x is 2, h of x is 1. So the range is that h of x is bigger than or equal to 1. So from that, we can then work out some properties of the inverse, because we need to remember, for the inverse function, the domain and range switch. So for the inverse, the domain will be what the range of h of x was. So the range of h of x was h of x needs to be 1 or greater. So the domain of the inverse is that x will need to be 1 or greater. And the range of the inverse function will be that the inverse needs to be less than or equal to 2. So using this fact, if we now square root both sides, we're going to get the square root of y minus 1 equals x minus 2. We can now consider plus or minus square root. So now, making x a subject, we need to just add 2 to both sides. So x equals 2 plus or minus, we'll leave this there for now, the square root of y minus 1. So the final step, once you've got x as a subject, we now replace x with h minus 1x. So therefore, h minus 1 of x equals 2 plus or minus, and then we replace finally the y for x. And I'll come back to this plus or minus in just a moment. I've not forgotten. So we want the range of h, the inverse function, to be 2 or less. So because of that, obviously it's going to start at least a value of 2. So therefore, we want the negative root only, because if we had plus root x minus 1, then also the range would be greater than 2, because the inverse would take a value eventually of something of a value bigger than 2. So we can now adapt this and switch the plus or minus for just simply a negative. So it's a subtlety, but an important subtlety to be considering the minus and positive options when we're square rooting, and in relation to this question, considering the domain and range. So we've not actually solved the question yet. All we have here is an expression for h minus 1 of x. h minus 1 of x, the inverse, is this here. So now what we're going to do is we set this equal to negative a half. So therefore, when is 2 minus the square root of x minus 1 equal to negative 1/2? So I'm going to add root x minus 1 to both sides, essentially, just switching it round. The square root of x minus 1 must be 2 plus a half, in other words, must be 5/2. If I now square both sides, x minus 1 must be 25/4, therefore x will equal 25/4 plus 1, which is 29/4. And that's question 6 done. Question 7 is about a small factory that's making bars of soap. So for this one, on any day, the total cost to the factory, Y pounds, of making X bars of soap is modelled by to be the sum of 2 separate elements, a fixed cost and also a cost which is proportional to the number of bars of soap that are made on that particular day. Write down a general equation linking Y with X for this model. Well, if it's a fixed cost, that means it's a cost which is never going to change. That's just plus some constant. So essentially Y will relate to X in some way. But this fixed cost, I'm going to call basically plus C, because it's just a constant. And quite coincidentally, C is the first letter of cost, which is lovely. And the cost which is proportional to the number of bars of soap that are made that day, basically I just need a constant, because a constant of proportionality in front of X. I can't say it any simpler than it's just going to be Y equals mx plus C, to be honest, where M is going to be the proportional cost, and the fixed cost is just going to be the y-axis intercept, C. So now using this idea, we can now infill into this linear model. So the bars of soap are sold for £2 each. And on a day when 800 bars of soap are made and sold, the factory makes a profit of £500. On a day where 300 bars of soap are made and sold, the factory makes a loss of £80. So use the above equation, show that y equals 0.84x plus 428. So it's always worth reminding us what on earth y actually is. Y is the total cost to the factory. And what we're saying here is about profits and loss. So we need to remember the admittedly quite basic formula for what profit is, but without thinking in these terms, we're going to be lost. So just to remind ourselves from GCSE or even before, profit is essentially money in minus money out. So who's going to get money in, or the factory are going to get money in from the sales, so sales which come in, and the money they pay out is going to be the costs. So we're using this formula for profit. And Y is the cost to the factory. So essentially, profit is the sales minus Y. So first of all here, we can use this formula and input information on this line. So they're sold for £2 each, and so on a day when 800 bars are sold, that's going to be £1,600 in sales. So if 600 bars of soap are sold, then the first formula we can get is that the profit, which is £500, must be the sales on that day, which is £1,600, because 800 times 2 gives 1,600, then minus the costs. So the cost, of course, is just in terms of y equals mx plus c, so we can rearrange. So the cost, if I add the cost to both sides, then subtract 1,100, that's going to be £1,100. But of course, the cost is what y is, that's mx plus c in this particular case. So we've got 1,100 equals mx plus c, but of course, in this particular case, if x is representing the number of bars, then x is 800. So 1,100 equals 800m plus c. The other day, we've got where 300 bars of soap were sold. And that particular time, they make a loss of £80. So whereas before it was a profit of 500, on the other day they make a loss of 80. So the other equation, we're going to get two equations to solve simultaneously, essentially, is what's going to happen here. We get minus 80 equals, for sales on that day, 300 bars times £2 each, that's £600, minus, of course, costs to the factory. So we can rearrange that to work out what the costs must be. The cost must have been 600, add 80, because minusing minus 80, essentially. The costs must have been £680, and that, of course, we can get in terms of mx plus c. So now, the costs, 680, that's going to be m multiplied by 300, because on this day, we've got 300m. X is 300, so mx is 300m. We've now got two equations we can solve simultaneously, and essentially, yes, that is exactly what we need to do. So if I underline these pair here, and then we're just going to solve them simultaneously. So you can do this purely algebraically, or using the calculators. A good A-level calculator should be able to solve linear simultaneous equations for you. So essentially I'm just saying here, solve these two simultaneously, where I mean the two underlined equations in red. So then what we're going to get, well, let's just do it together, in fact. So on this particular model of a class whiz, which is my favourite, to be honest, we go to menu, and then we're going to go to the equation solver. So we go to equation slash function, press equals. We want a simultaneous equation, so it's option 1. Number of unknowns is 2, it's just m and x. So the first equation we can use, so we've got 800 m's plus 1c. So these x's and y's are dummy variables, essentially. So in our case, the x, which is going to be solved, will be our m, and the c for us is going to be the y. So the first equation here, we set that equal to 1100. And the next one, we've got 300m, but we need to use x, plus 1c, so put y as being 1. That was equaling a cost of 680. So press equals. We get that x is 21 over 25, which essentially is 0.84. So therefore m is 21 over 25, which is 0.84. By the way, it does say show that, so you need to be clear that you've solved these simultaneously. I would state that you've used your calculator, for example. I'd really make it clear that you have solved these simultaneously. You can't just pull out of thin air m is 0.84. You need to give evidence to the examiner what process you followed to arrive at this conclusion. So m is 0.84, and then of course if I go back to the calculator, press equals again to get c, it's a relief to see that c is indeed 428. So therefore m equals 0.84, c equals 428, and so, as we wanted to show, y is 0.84 plus 428. 0.84x, of course, I mean to say. Part C, it says, with reference to the model, interpret the significance of the value 0.84 in this equation. In this case, because it is a linear model, I think it may well be useful to just sketch out what's happening to make sure you don't make a little error with part C. So the actual equation now we've got, it's y equals 0.84x plus 428. If we were to graph it, we'd have something looking like this. So 428 would be essentially the y-axis intercept, and m, which I've called it, is the gradient. So in terms of what the gradient means, going back to GCSE and before, in fact, it just means the change for each unit increase in x. It's a change in y each time x increases by 1 unit. So think about the x units. X is basically the number of bars of soap. So for each extra 1 bar of soap we make, the cost to the factory increases by £0.84. So in other words, it's telling us the cost to the factory for each extra bar of soap. So the wording I'd suggest to use would be something like this at the bottom. So essentially it's to say that 0.84 is the cost to the factory for making each extra bar of soap. If you're wondering why I'm using the word extra, essentially it's because I can't just say that the cost to the factory for making one bar of soap would be 84 pence, because the fixed cost is £428. So by using the word extra, I'm saying what the price is going up by each extra time a bar of soap is added. So it's going up in increments of 84 pence for each extra bar of soap that is added onto the production queue. It's not to say necessarily that to make one bar would be 84 pence. So I'm just being a bit careful of the wording there to make sure the examiner's got no excuse to dock me a mark. Finally, part D. Assuming that each bar of soap is sold on the day it's made, we need to find the least number of bars of soap that must be made that day on any given day for the factory to make a profit for that day. Well, if profit means sales minus costs, then if we're finding the least number of bars of soap that must be sold on a particular day, we're after the crucial point where we're about to break even. So the critical point is where the sales would equal the costs to the factory. So if I set sales equaling costs, then we can go from there. So if X is, of course, the number of bars of soap which gets sold, and each one we sell for £2, then the sales will be 2x, and the costs to the factory, using this linear model, of course, will be 0.84 multiplied by the number of bars we're using, which is x, plus 428. So it's a very simple rearranging of this equation, to be honest. We just need to subtract 0.84x from both sides. So that will give us 1.16x equals 428. Therefore, divide this by 1.16, and that gives us what x is. So 428 divided by 1.16, that gives us a value of 368.97. Now we need to evaluate this figure if it makes any actual meaningful sense. We want the least number of bars of soap that must be made on any given day for it to make a profit. So actually, we want to just be making a tiny bit of profit, not making any loss. So what it's saying here is, to make exactly to break even, it'd be 368 and a bit bars of soap, almost 369. So 368 bars, you'd be making a slight loss. If I rounded this up to 369, it'd be a profit of literally maybe a couple of pence. So I need to round this up, not just because it's 0.5 or higher, but because we're needing a profit, essentially. So therefore, we're needing 369 bars to be sold. And that's question 8 wrapped up. No, it's not, it's question 7, because I can't count. Sorry, that's question 7 done. Question 8, sequences and series. So 8 part 1, we're to find the value of 20 multiplied by a half to the power of a half. Sorry, to the power r. I'm going to explain a few different steps you might want to take for this one. What you could do, which I think is quite useful, is you could actually generate the first few terms of the sequence. And so what I'm going to do here, I should say the sequence, imagining r starting from 1. If r started from 1, the first value, of course, would be 20 times half to the power 1, which is just 20 times a half, which is 10. When r is 2, it's going to be 20 times a half squared. Half times a half is a quarter, 20 times a quarter is 5. Each time we increase r by 1, we're multiplying by a half again. To multiply by a half is the same as dividing by 2. So to just give you a feel for the pattern, it's something like this. So 5, then 5 halves, which is 2.5, 5 quarters, the next one will be 5/8. Then I'm just going to go dot, 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 dot. And so again, as I say, there's a few options for how we can think about this question. But if I just put this in a thought bubble here, what this means is we're starting here from 0.625 and then adding onwards. And so the initial figures of 10 plus 5 plus 2.5 actually aren't a thing here. These are like ghost figures. So this sequence here, what we're actually trying to sum is actually only starting from 0.625. In fact, I could have called that 5/8. Of course, that's on 5/16, 5/32, and so on. So essentially what I'm trying to say here is this sum is the same as the sum from r is 1 up to infinity of 20 times half to the r minus what we'd get if we summed from r being 4 up to infinity. So from r being 1 up to infinity, there is a formula for the sum to infinity. So if I just remind you what it is here, the sum to infinity is a over 1 minus r. And as well, there's also some of the first n terms of an arithmetic sequence. So the first n terms, it's similar to this equation really. It's a brackets 1 minus r to the power n all over 1 minus r. So in our case, the first term would have been 10, okay? But of course, because we're summing from 4 onwards, we're just looking at all of this. So using this formula here, this is from r being 1 up to infinity. So the sum of the first r terms to infinity is going to be a, which the first term would have been 10, over 1 minus r, common ratio is a half. Then we're going to minus away 10 lots of 1 minus r, which is a half to the power 3. So 1 minus a half to the power 3, I can either just do a half cubed or just say it's 1 over 8, again over 1 minus a half. So if we just do these on the calculator, because it's fairly standard really. So 10 all over 1 minus a half. In fact, we know 1 minus a half, of course, is a half, so we can just double the tops. So we've got 20 minus 20, brackets, 1 minus 1/8. And what we'll have here is just 5 over 2. I'll also show you another way you could have used the calculator to do this. So by writing out the first few terms and seeing that the first 3, if you started from 1 instead of 4, would have summed to 17.5, there's actually on most calculators a summation function. So on this version of ClassWiz, it's this one here. So if I were to type in 20 multiplied by, this is in terms of x, not in terms of r, but it's the same idea. So now it's going to be 1 over half to the power x. So shift and then x, where's the x? So alpha x rather, and put in from x being this time. In fact, we could have done even from 4. So if we did from 4 up to a high number, for example, say 80 or something like this to give it time to converge. 80 might not seem big enough, but this is going to shrink down to very small values very quickly. So let the calculator think and just do its thing. you get exactly 5/2. So it's already converged so accurately, but it's 5/2 plus or minus barely anything whatsoever. Hence, even rounded, it's give it exactly. So if you tried smaller values, you'd see it going towards 5/2. So that's just indication. At worst, it's a vindication of your answer 5/2. At best, because the examiner isn't saying here you must show that or use a particular method, the question is literally just find the value. You found it, and that's a really easy free marker if you know that sort of tip with a calculator. That's a massive, almost hack, really. Part B, show that. So this one is a show question, so we can't just rely on the calculator. From 1 up to 48, the sum of log base 5 of n plus 2 over n plus 1 equals exactly 2. So what we need to do here is to write this out longhand to establish to ourselves and to the examiner a pattern which we can then manipulate. So down from 1 to 48, log base 5 of n plus 2 over n plus 1. That, of course, if we just do it slowly but surely, we'd get log, when n is 1, n plus 2 is 3, n plus 1 is 2. So it's going to be log 3/2. The next one will be plus log 4/3, and so on, and so on, and so on, until we get to the last one, where n is 48. The last term, I should really say log base 5. The last term would be 48 plus 2, which is 50, and then 48 plus 1, which is 49. Now, so far, this doesn't look particularly helpful. However, if we just think about the laws of logs, the log of one thing over another is the same as log of that thing minus log of a denominator. So log base 5, 3, minus log base 5, 2. That's what the first term would be. The second term, splitting this into two separate logs, will be log base 4, sorry, log base 5, 4, minus log base 5, 3. And keep going and going. So the next term, next two terms rather, would be log base 5 to the power 5 minus log base 5 to the power 4, and so on and so on. If I now do the penultimate term, when n is 47, the penultimate bit would be log base 5 of 49/48. And the final log, this one, gives log base 5 of 50 minus log base 5 of 49. So here we can now have a look and see if we can spot the cancellations. So this one here, we can see log base 5 of 3 will cancel with this log base 5 of 3 here. Log base 5 of 4 will cancel with that one. This log base 5 of 5 would cancel with another one down here, so that again would cancel somewhere in the middle. Log base 5 of 49 cancel this end one, and log base 5 of 48 would have cancelled with something before here. So actually, all we're going to be left with at the end of all of that is just what hasn't cancelled, which is the log base 50 and this negative log base 5/2. So we can say we just end up with log base 5 of 50 minus log base 5 of 2. And then if we put it back into a single logarithm, that's the same as log base 5 50/2, which is log to the base 5 of 25. Then what power of 5 do I need to raise 5 to get the answer 25? Of course, that is 2. And that's question 8 finished off. Question 9 involves a research engineer who's testing the effectiveness of a braking system of a car when it's driven in wet conditions. The engineer measures and records the braking distance d meters when the brakes are applied from a speed of v kilometers per hour. Graphs of d against v are shown, so this is d against v, and also log base 10 of d against log base 10 of v. over here were plotted. So one is obviously linear, the other is non-linear. So what we need to explain for part A is how figure 6, this linear graph, would lead the engineer to believe that the braking distance should be modelled by the formula d equals k multiplied by v to the power n, where k and n are constants, with k approximately equal to 0.017. The suggestion for this question would be to start with the premise that, okay, let's assume that this engineer is correct. So what if it could be modelled by d equals kv to the power n? So if d did equal kv to the power n, then what we could do is take logarithms of both sides. So we'd have log base 10 of d equals log base 10 of kv to the power n. Now, using the laws of logs, this could be separated into two separate logarithms. So log base 10 of d would equal log base 10 of v to the power n plus log base 10 of k, because the log of a product is the same as the separate logs of those things added together. In a similar way, this here is also subject to a log law of its own. V to the power n, that n can come to the front and becomes the same as n multiplied by log 10 of v. So the next step, we have this. What we can now do is think about this in a bit more depth. So the suggestion I'm going to make here is that we can compare these variables to a straight line graph. So log base 10 of d in blue, that's a variable, it's the y-axis. N is just a constant. Log base 10 of v, that's a variable as well along the x-axis. And log base 10 of k, because k is a constant, this will be a constant as well. We can now compare this to the good old-fashioned y equals mx plus c. As you can see here, it has exactly the same format. Variable equals constant multiplied by a variable plus constant. So this would give a graph of y equals mx plus c, which, as we know, is the standard equation of a straight line graph. So essentially, we've got it into the correct form. All we need to do now is to conclude correctly. So therefore, a graph of log base 10d against log base 10 of v would be linear. Figure 6 is linear, so because it's linear, this does support the engineer's belief. And to go a bit more in depth, because part A asks us about k being approximately equal to 0.017, then if this were like y equals mx plus c, which of course it will be, then the y-axis intercept is going to correspond to log base 10 of k. And we're told here that the y-axis intercept is minus 1.77. So in other words, log base 10 of k must equal minus 1.77. We can of course solve this, so rearranging this to work out the value of k, k will therefore be 10 to the power of minus 1.77, which is 0.01698, and so on, which does approximate to two significant figures to 0.017. So that shows, again, that k is about 0.017 in agreement with this engineer's belief. So finally, to conclude, that this does round to 0.017, and then we're done part A. Part B is to use information in figure 5. So we're going to use this coordinate pair here, 30 and 20, with k now being 0.017. We're going to find a complete equation for the model, giving our value of n to three significant figures. So from before, we had log base 10 of d equals n log base 10 of v plus log base 10 of k. So we can transform this, essentially. So log base 10 of d, I'm just underlining here, d is essentially like the y-axis input, v is the x-axis, if you like, and log base 10 of k is log base 10 of this value, and this corresponds to the y-axis intercept. And so if d corresponds to the y-axis and v corresponds to the x-axis, then essentially our x, or v if you like, is 30, and our known value of d on the y-axis is 20. So we can substitute these values in to work out the value of n. So therefore, log base 10 of 20 is the same as n log base 10 of 30 plus log base 10 of 0.017. We can now rearrange this to get n log 10 base 30, n log base 10 of 30 on its own. So if we subtract log base 10 of 0.017, we arrive at this. We can then, of course, divide all of this expression on the right through by log base 10 of 30 to get what n is. So this awkward number here is 3.07 and so on. So if we now divide this by log base 10 of 30, we'll get that n is 2.0787, which rounds to three significant figures to 2.08. So n equals 2.08, correct to three significant figures. The complete equation for the model, we now use this value of n in terms of our models for this relationship. So we could have it in two different forms, in fact. Using this first form here, if we just substitute in that n is 2.08, this here becomes log base 10 of d equals 2.08 log base 10 of v plus log base 10 0.017. However, perhaps a more useful formula, because this second one gives us d as a subject without having to undo the fact it was logged, d equals 0.017 times v to the power 2.08. So that just returns to the model mentioned in part A of this question. We can now have a look at part C. So part C of this question. So part C, Sean is driving his car at 60 kilometers per hour in wet conditions when he notices a large puddle in the road 100 meters ahead. It takes him 0.8 seconds to react before applying the brakes. So use a formula to find out if Sean will be able to stop before reaching the puddle. So reminding us what we had before in a second. I'll put this on in a moment. The stopping distance, by the way, is the thinking distance, because before you even brake, you need to think before you brake, and then of course the distance travelled as you're braking once you've realised you need to brake. So it says here, his thinking time rather, is 0.8 seconds. So it takes him that much time to react before he brakes, and before he brakes he's travelling at 60 kilometers per hour. Now we need to convert this into meters per second first of all. So first of all, 60 kilometers per hour and 0.8 seconds. Well, 60 kilometers per hour, if I times that by 1,000, I get it in terms of meters, then divide by 3,600 to convert from hours into seconds. That gives us 50 over 3 meters per second, so 16.6 recurring meters per second. We then also need to work out how far he's travelling at this speed. So he's travelling at this speed for 0.8 seconds, therefore the distance covered is this value multiplied by 0.8, which is 13.3 meters. Now to work out his braking distance, we can use a model we've derived from part B. So the braking distance, using the model from part B, d for the braking distance is 0.017 multiplied by the velocity to the power 2.08. So plugging in the numbers here, now v is in kilometers per hour. That's what the model actually says, look. So we keep the v in terms of kilometers per hour, so keep it 60, and the value of the power here was the value of n we found in part B. So plugging in those values, we get the braking distance was 84.9 meters. That gives a total stopping distance of 13.3 plus 84.9, and that comes to a total stopping distance of approximately 98.2. Sean, though, sees a large puddle which is 100 meters ahead. So will he stop before reaching the puddle? Well, it's going to take him about 98 meters to stop. The puddle's 100 meters ahead. So importantly, he can stop before the 100 meter point because this value here is less than 100. So he's got about 2 meters to spare. So it's a close shave, but essentially the answer is he can stop in time. So the conclusion we make is simply to say Sean will stop before reaching the puddle, assuming this model, of course, holds true. Question 10 is about vectors. So figure 7 shows a sketch of triangle OAB as shown. Point C is such that from O to C is double the length of from O to A. And so O to C essentially is twice the magnitude of vector from O to A. So we can picture this on this diagram here, in fact, if we like. So geometrically, if from O to C is double the magnitude of O to A, we could picture C being here, double the distance away from O than what A is. So imagine C here. And as well as that, if from O to C is twice the length of from O to A, then this length here from O to A must be one the same as the length from A to C. So that's worth mentioning as well. the distance AC is the same as the distance OA. So therefore the vector from A to C will also be the same as the vector from O to A. M is the midpoint of the line AB. So if I add in M here and just pop in its point like so, it then says the straight line through C and M, so we're going through like this, cuts the line OB at the point N. So if I add this in a green dotted line, and the point N will be somewhere down here like so. We're also told that from O to A is vector A, and from O to B, we're going to label that as vector B. So in terms of colour coding those, if I just add in vectors parallel to O to A in a red colour, and vectors parallel to OB in a purple colour. So first of all, what we need is to find the vector CM in terms of A and B. So like I say, just adding in OB in purple like so. Now CM is going from this point here down to M, and we don't know any vector that tells us a direct route, so we can't just go from C to M directly. What we'd need to go is from C down to A, and then from A, and then we can think about how to get from A to M. So the first step is to think from C to M, I can go C to A, and then from A to M. So how could I go from A to M? Well, A to M is half of the distance from A to B. So AM is the same as half of from A to B. So I can fill this bit in. AM is the same as half of AB, and from C down to A, that's the same magnitude as vector A, but again in the opposite direction, so this is minus A. So AM, which is half of AB, how do I go from point A to point B? I'd have to go from A to O, and then from O to B. So I can replace AB with AO plus OB next. AO is of course parallel to vector A, but in the opposite direction, this is going to be minus A, and from O to B, that's just going to be vector B. So if I fill in this with the actual algebraic vector notation, I arrive at this result. I'm going to have minus A plus half of minus A for AO, and OB is vector B. If I now expand this out, I'm going to get minus A minus another half of A, so minus 3/2 of an A plus half of a B. And that's the final answer. Or if I want to, what I could do is factorise out the half. Optionally, I could have also said C to M is a half of B minus 3A. For part B now, we need to show that from O to N is this relation here, where this lambda is a scalar constant. So lambda is just a number essentially. So it's a constant number, just like M is a constant number for the gradient of a straight line. So what we need to do for this one is to think how I can go from O to N. Now from O to N, obviously that's just along vector B, but if you see here, I need to involve A components and B components. So the clue here is, can I find a route from O to N that uses a red route along the A components and utilizes B? So is it going to use from O to B in some place? So let's just think about using the red first. Okay, so to go from O to N, what I could do, I could go up from O to C. Then when I'm at C, I could then go from C back down to N. So I can say that O to N is OC, and then from C down to N. But from C to N is going to be some multiple, I'm going to call it lambda, is some multiple of CM, because CM and CN are collinear. They lie on the same straight line, and so CN is just some multiple, I'm going to call it lambda, of the shorter one, CM. So then just let's think about what OC is. Well, OC is of course 2 lots of A, but CM from before, we can use this expression here. So CM is the same as this over here. So therefore O to N is 2A plus lambda lots of CM, which is this expression here from part A. If I now expand all this out, times everything in the brackets by lambda, I now get this result. I get 2A minus 3 lambda over 2 lots of A plus half lambda lots of B. My target is this here, so I need to factorise out anything, any coefficient of A and any coefficient of B. For coefficients of A, you can see I've got 2 minus 3 lambda over 2, which is what I want, and then for the b, just half a lambda. So we've got what we need, just write it in the correct form, and we've got it in what we needed to show. Part C, we're going to use part B to prove that this point N splits OB in the ratio 2 parts to 1 part. So first of all, because ON is parallel to vector B, which is self-evident really, O to N is along this B line, has nothing to do with A, the vector ON will have no A component. A is going sort of diagonally up, so this bit here will be 0, and that's our clue, our way in to solving this question. So using part B, the expression from part B, realise you have no A component, this bit of it here will be equal to 0. So, if 2 minus 3 lambda over 2 is equal to 0, this can be fairly easily solved. If I double both sides of this equation and get 4 minus 3 lambda equals 0, then add 3 lambda to both sides and divide by 3. Lambda is, of course, 4/3. We can now substitute this value of lambda into this expression in part B for what ON is. So ON now becomes this. 2 minus 3/2 of lambda, which is 4/3, so minus 3 over 2 times 4/3, lots of A, plus a half lambda becomes plus half of 4/3 of B. Now, because we said there's no A component, this here is just going to obviously vanish. If you want to, you can work it out with your calculator, but this would equal 0. So you can cross this out essentially and just focus in on what B is. The coefficient of B is a half times 4/3, which is 2/3. So therefore, from O to N is just 2/3 of the total length from O to B. So this bit ON is 2/3 of the distance, therefore NB will be the other 1/3. So the final conclusion is to say, therefore ON as a ratio to NB is 2/3 to 1/3. If I then multiply both sides of this by 3, it then is quite obviously the same as the ratio 2 to 1. So therefore ON to NB is in the ratio of 2 to 1, which we required to prove. We have done, so that's question 10 completed. So figure 8 shows a sketch of a curve C with equation y equals x to the power x, where x is greater than 0. Find, by firstly taking logarithms, the x-coordinate of a turning point of C. So turning points, you should be thinking of differentiation essentially, finding the derivative. So what we need to do is to differentiate this equation. And so essentially what we need to do is to differentiate both sides. So if we start with y equals x to the x, we can take logs of both sides and get ln y equals ln x to the x. In other words, I can now bring this power to the front using the laws of logarithms. So ln y is going to equal x multiplied by ln x. So now if we differentiate both sides, then what we need to do on the left-hand side is to differentiate this implicitly, because it's a function of y. So to differentiate implicitly, it's very much the same as if it were a function of x. So if it's ln x, what we do is differentiate and put it as 1 over x, but because it's a y, we're going to get 1 over y. And then if it's a function of y, we just stick a dy by dx on the end. So 1 over y, dy by dx. And over here, this is going to be using the product rule for differentiation. So I'm going to differentiate the x to 1, leave the ln x as it is. So I just get 1 lot of ln x. Now I'm going to leave the x on its own and differentiate ln x. And ln x differentiates to 1 over x. So that obviously simplifies to ln of x plus 1. Now if I multiply both sides of this by y, what I'm now going to get is that dy by dx, that's not quite straight, which is slightly annoying. There we go. So dy by dx is going to be y multiplied by ln x plus 1, and that's going to equal 0 at the turning point. If I just put TP as turning point, that way it's not going to be that confusing. So is y ever 0, as you can see from this graph? Well, y is never 0, y is always greater than 0. So what we now need to do is to solve for when ln x plus 1 is equal to 0. And this is actually not too hard to do. So ln x plus 1 equals 0. So ln x equals minus 1. So therefore, x is simply going to be e to the power minus 1 at that turning point. So x equals e to the power minus 1 at the turning point. So that's part 1 of this question complete. We can now start thinking about part B, and then of course part C after. Part B, we're told that the point P, which has x coordinate alpha, y coordinate 2, lies somewhere on C. And we need to show that alpha is somewhere between 1.5 and 1.6. So what we need to do here, essentially, is to spot that this curve is continuous. It's got no curves or asymptotes, and so we need to know that if we find a solution and the curve's continuous, then if we try 1.5 and it's, for example, lower than 2, then we go to 1.6 and it goes above 2, that will prove there's a solution between 1.5 and 1.6, because it can't go below 2 to being above 2 without going through 2 if the curve is continuous, which is what it is. So first of all, what we need to do is to try 1.5 to the power 1.5, because that is the lower bound of alpha. So 1.5 to the power 1.5, it'd give us 1.837 and so on, which is less than 2. So essentially, what we've tried here, we've tried 1.5 and it's a bit less than 2. So if I were to draw this on, for example, so if I just show you where this might be. So for example, 1.5 for x might be here. So if x is 1.5, that's given us that the y value is about 1.8. Next, what we try is x being 1.6. 1.6 to the power 1.6 is 2.1212 and so on, which is actually more than 2. And so to show you this one now, imagine that being 1.6. That gives about 2.1. And so the value of 2 itself must be about here. As you can see, the x value that corresponds to y being 2 must fall between 1.8 and 2.1. So x must be in between 1.5 and 1.6. So to conclude, we just have to say these key things. There's a change of sign in between 1.5 and 1.6. We're going from being below 2 to more than 2, and the function is continuous on the interval from 1.5 to 1.6. Really crucial, we say it's continuous. So these two pieces of information, there's a change of sign from being below to above, or it could have been from above to below, and the function's continuous. We can conclude and say the root, therefore, must be in between the two values we've checked. So alpha is between 1.5 and 1.6. Now, we could use a possible iteration formula that finds alpha exact. So one possible iteration formula is x subscript n plus 1 equals 2 lots of a previous value of x to the power of 1 minus that previous value of x. So we're going to use this formula with the first value of x being 1.5. We're going to find x to the power 4 to 3 decimal places. So I'll show you how to do this quite quickly. So we're going to have 2 times x, which is 1.5, to the power of 1 minus that value of x. So we type this in, we press equals, we get 1.6329963, sorry, 632993162. So the first time we use this formula, we're going to get this. The x subscript 2 is this value here. Now the next one, x subscript 3, we're going to input this value now in terms of the previous value of x. So x subscript 3 we can generate manually like this, where we've got 2 lots of the previous value to the power of 1 minus the previous value of x, which gives this. And then x subscript 4, we'd use this value, 1.466, to find x to the power 4. So x to the power 4 is going to be this. So we've got two lots, so I'll just fill this in. It's not copied through correctly. It's got two lots of that, which gives 1.673135301. But to use your calculator more efficiently, what we can do once we've got the first value is we can just switch x subscript n to ans. So if I were to type in here just simply ans, and that being ans as well, then the next one on my calculator display just had x subscript 2, the next one will be x subscript 3, which is indeed 1.466. Press again for x subscript 4, and that's how we get the 1.673135301, much quicker and much more efficiently. Part D, we're asked to describe the long-term behaviour of x subscript n. Now we do have a calculator in our hands, so what we can do here is use this to our advantage. So if we keep pressing again and again and again, that's going closer to 2, the other value is going closer to 1. So what happens eventually is we get this. It goes 2, 1, 2, 1, 2, 1, and it alternates. So the long-term behaviour, this sequence x subscript n, becomes periodic. It oscillates in between 1 and 2. So in order to get your marks, you need to say something like this. The long-term behaviour, xn, ends up oscillating in between the values of 1 and 2. It becomes a periodic sequence of period 2. It oscillates between two values, 1, 2, 1, 2, 1, 2. There's two different values between each repeat of the oscillation, so it's period 2. Importantly, it's this last bit here we need to say. It becomes periodic of period 2, and if you want to say, it varies. It oscillates in between 1 and 2 each and every time. Question 12, you need to prove this trigonometric identity. Cos 3 theta over sine theta plus sine 3 theta over cos theta equals 2 lots of cot 2 theta. We've got this restriction on theta. It can't be equal to 90 multiplied by n. Otherwise, that would give a denominator equal to 0, which wouldn't be defined. So that's why the restriction's here. But we don't need to get too caught up with this. What we need to do, really, is to start with the left-hand side and to manipulate it step by step so it becomes the right-hand side. So let's just start off by writing out what we've got. So we've got cos 3 theta all over sine theta plus sine 3 theta. Sorry, sine 3 theta, I mean to say, all over cos theta. Now, if adding two fractions together, this even goes back to GCSE really, we can just multiply both denominators by their opposite counterpart to make sure that we get a fraction which we can then combine into one. So if I multiply top and bottom of the first one by cosine theta, and the top and bottom, numerator and denominator, of the second fraction by sine theta, then we're going to get this. The first fraction and a second fraction. The first one is going to become sine theta multiplied by cos theta, so I just write this in. So I've got sine theta times cos theta. And then this one, if I'm multiplying by cos theta, I'm going to get cos 3 theta times cos theta. So cos 3 theta times cos theta. Then I'm going to add on the second fraction. Because I'm multiplying top and bottom of this one by sine theta, this other one's going to become sine theta times a cos theta, which was there before. And this time, I'm multiplying the top one by sine theta. I'm going to put the sine theta last, so hopefully you can see a pattern with the numerator. So at the top, I'm going to get sine 3 theta times sine theta. So this can now be combined into a fraction with a single denominator, because now I've got sine theta cos theta on both numerator and denominator. However, we need to think about what we can do at this top. So I've got sine theta cos theta on the bottom. At the top, I've got cos 3 theta, cos theta, plus sine theta, sine theta. So it's cos cos plus a sine sine, where I've got two different size amounts here relating to the angles. So we need to be thinking of compound angle formulae for this one. I've got it here from the formula book. Cos A minus B, if I have a look at this bottom one here, cos of A minus B is cos A cos B plus, which is what we've got here, a sine and a sine. So what this tells us here is essentially that what we had here, cos 3 theta cos theta plus sine theta sine theta, that's the same as cosine of 2 theta. So essentially, what we can say here is cos of 3 theta minus theta, which is the same as this thing here. That's the same as cos 3 theta times cos theta plus sine 3 theta sine theta. So that's what we have on the top of these fractions. But of course, if that's equal to cos of 3 theta minus theta, 3 theta minus theta is the same as just 2 theta. So that's the same as cos of 2 theta on the top, based off this identity as given in the formula book. Now, the bottom here, sine theta, cos theta. Now, that's almost a double angle formula. We need to know that sine 2 theta is 2 sine theta cos theta. This is just 1 sine theta cos theta, so the bottom is the same as a half of sine 2 theta. And the top I can now leave as cos 2 theta. Now, if I'm dividing by a half, that's one and the same thing as multiplying by 2. So I can just put that 2 on the top. So I'm going to get 2 lots of cos 2 theta, all divided by sine 2 theta. Now, cos over sine is the same as cot, and so cos 2 theta over sine 2 theta will be cot 2 theta. I've got 2 lots of that, so that's exactly what I wanted to prove. And to be strictly robust, what I should really say here is use identity symbols, so we're consistent with the actual question, because these aren't just equal, these are always one and the same. So cos over sine is cot, so we've done it. So that's the same as 2 cot 2 theta. We're now going to use this for part B of question 12. So for part B, we're going to now solve a trigonometric formula. For theta in between 90 and 180, we need to solve this here. Now, this thing we've shown is one and the same as 2 cot 2 theta. So our first step is to just replace this with 2 cot 2 theta. So 2 cot 2 theta is the same as 4. That's our first step. I'd now suggest just divide by 2. So we get cot of 2 theta equals 2. Cot is 1 over tan, so therefore tan of 2 theta equals a half. We can now work out the principal value. So 2 theta, not theta but 2 theta, is going to be tan to the minus 1 of 1/2, and let's see what that gives us. So calculator to hand, tan minus 1 over half, so shift tan, put a half in, close brackets, we get 26.565. Now, here, This is our range for theta. I'm talking about 2 theta, and so the range for 2 theta, because 2 theta is double theta, we need to double the limits. So the range for 2 theta is from 180 all the way to 360. And so 26.565 isn't in range. So what we now need to do is to use a cast diagram. I've got one over here. So this here, this angle, it'd be 26.565, which obviously isn't enough. So I need to go around to where tan is again a positive value, which is in the T quadrant. So 26.565 plus another 180 gives that 2 theta must be 206.565. Now we can't go around again because then we go beyond 360, which would be out of range. But we've got that 2 theta needs to be this value, and that's for any solution we've got. So therefore we need 2 theta to be equal to 206.565. But we don't want 2 theta, we want just 1 theta. So therefore theta, if we now divide that by 2, so add 180 onto it to get it in range, divide by 2, and to 1 decimal place is going to be 103.3 degrees. So theta is 103.3 degrees. Question 13 is about a manufacturer making a storage tank. So it's modelled as in this diagram in figure 9. It's in the shape of a hollow circular cylinder, closed at one end, with a hemispherical shell at the other end, like so. The walls can be assumed to have negligible thickness, so they're not going to affect the calculations. You don't need to consider how thick they are or aren't thick. The cylinder's got radius r meters and height h, and the hemisphere has radius r meters too. The volume of the tank, we're told, is 6 cubic meters. And for part A, we need to show that according to the model, the surface area of a tank in square meters is given by this expression here. So let's set to it. So the surface area of this shape is going to be comprised of obviously different bits. It's going to have the curved surface area here, which is going to be circumference multiplied by the height. Circumference is 2 pi r and height is h. So the curved surface area is going to have an area of 2 pi r h. That's the curved surface area. We're also going to need the curved surface area of the shell on the top. Now, this is basically half a sphere, it's hemispherical. The curved surface area of a full sphere is 4 pi r squared. Because this is a hemisphere, the curved surface area of this one is half of 4 pi r squared, which is just 2 pi r squared. And finally, there's also a circular base. This will just have an area of pi r squared. But we're also told that the volume is 6. So the volume of this tank is 6. So to the side, what I'm going to do here is just to be thinking about how we can eliminate h, because h doesn't appear in this expression, but it does what we've got here. So maybe we can use this information to eliminate h. So let's just consider this. So if the volume of the tank is 6 cubic meters, well, the volume of this tank is going to be the volume of a cylinder, which is pi r squared h, plus the volume of the hemisphere, which would be 2/3 pi r cubed, and that must equal, therefore, 6. So what we could do here is to simplify this a fair amount, in fact. So what we could do would be to have h on its own. So if I now take this and we work it, I'm going to have pi r squared h is going to be 6. Then I can subtract this 2/3 pi r cubed from both sides. Then to get h on its own, I can then just divide by pi r squared. So therefore, h is going to be 6 minus 2/3 pi r cubed all over pi r squared. So we can use this in a moment. So if we now plug this in to what we have over here, we can now think about neatening it up after. So this is going to become 2 pi r multiplied by everything in the highlighted yellow. So it's 2 pi r times 6 minus 2/3 pi r cubed all over pi r squared. And 2 pi r squared plus another pi r squared, I can fairly easily just simplify that to 3 lots of pi r squared. So now what we can do is simplify this fairly awkward expression here. So if I were to basically just neaten this up, basically this denominator, dividing by pi and timesing by pi will cancel, and dividing by r squared and timesing by an r is the same as just dividing by 1r. So I'm going to take this 2 to essentially double all the top, so I'm going to have 12 minus 4/3 pi r cubed. That pi and that pi will cancel, and then I'm going to divide this all by r, like so, then plus 3 lots of pi r squared. This fraction I can now split into 2 parts. I'm going to have 12 over r. This bit now will become minus 4/3, then pi r cubed divided by r will simplify to just 4/3 pi r squared. Plus, of course, the 3 lots of pi r squared. And then we've got it, because 3 is the same as 9/3, so 9/3 take away 4/3 does indeed leave us with 5/3. So we get 12 over r plus 5/3 of pi r squared, which is exactly what we wanted to prove, and so we're done. We can now think about answering part B using part A to help us. So part B, the manufacturer needs to minimize the surface area of the tank. So we need to use calculus to find the radius of the tank for which the surface area is a minimum. So it's going to be a minimum when dA by dr is going to be minimized. So let's just set to work think about that. So it's going to be minimum when dA by dr equals 0. So I need to differentiate the surface area with respect to r and set it equal to 0. So we'll differentiate with respect to r this thing here. So 12 over r, I'm going to say it's 12r to the minus 1. And then 5/3 pi r squared I can leave as it is. 12r to the minus 1 will differentiate to minus 12r to the minus 2. And this here, the 2 will drop to the front, so the 5/3 becomes 10/3, and I get 10/3 of pi times r. And then I say that's going to be equal to 0 at the minimum, using this fact here. So what to do with this? Well, my suggestion now would be to multiply through by r squared. So if I times both bits by r squared, what I'll now have is essentially 10 thirds pi r cubed. If I put the positive term first, 10 thirds pi r cubed. 12r to the minus 2 times r squared becomes just 12r, so I just get minus 12. So r squared times r to the minus 2 cancels. Sorry, I'm listening to say this becomes minus 12. So get minus 12 equals 0. So therefore, this can be rearranged quite straightforwardly. If I add 12, divide by 10 thirds pi, and then cube root the whole thing, I'll have what r is. So r is going to be 12, then divide by 10 thirds pi, all cube rooted. If that's too awkward, you can do this in a few different steps, which I'll show you now. So what I'm going to do first, I'm going to add 12 to both sides. If there's too many steps, so if I add 12 to both sides, I get 10 thirds pi r cubed equals 12. I can then times by 3. Then I get 10 pi r cubed equals 36. Then if I divide by 10 pi, I get that, and then I need to cube root. And so shift cube root my answer. I get 1.04644 and so on. So 0.46, my mistake. And that, of course, just becomes, when rounded to a better degree of accuracy to 3 different figures, I get 1.05. Now, part C of this question, I just need to calculate now the minimum surface area of that tank, giving my answer to the nearest integer. So surface area is basically just going to be the answer we just had. So it's 12 divided by 1.0466 plus 5 over 3 times pi times that value squared. And because we've got a calculator, we can do this very efficiently. Essentially, we've just worked out the radius which will generate the minimum surface area for the cylinder. So we have r stored into our calculator memory. So if we type in exactly as it looks and replacing r with the ans function, in other words, our stored r, which is exact, so 12 over the answer plus 5 thirds of pi times the radius squared, which is my previous answer squared. This will give us exactly the surface area of that tank. I get 17.201 and so on and so on, which seems reasonable. But now we need to just look and be thinking what we need to give our answer to is to the nearest integer. So to the nearest whole number, that gives 17. So the surface area to the nearest whole integer is 17 square meters. Question 14 is an integration by substitution. So we're told that u equals 4 minus root h, so I'm going to begin by just writing that out. So u is 4 minus root h, but I'm going to call that as being h to the 1/2. So that's what u equals. What I could do with working out next is a few things, namely du by dh. So if I differentiate this with respect to h, that's going to be a good thing to do because I need to work out what dh is in terms of du. So differentiate this with respect to h. The 4 will obviously disappear. That half will come to the front, so I'm going to get minus 1/2 h, then the half will decrease in power by 1, so a half minus 1 is minus 1/2. If I now multiply both sides by dh, and I get that du equals minus 1/2 h to the negative 1/2 dh, If I now multiply by -2, I get negative du equals h to the -1/2 dh. Then finally, dividing both sides by h to the -1/2, I'm going to get that dh equals -2 h to the +1/2, because if I divide by h to the -1/2, it comes out as being +1/2. So I worked out what dh is. So dh, which of course appears here, dh is -2 h to the +1/2 du. As well as this, you might also see that we've got a root h on its own to contend with, and we can work out what root h is by just rearranging what u is, because u is given in terms of root h. So in other words, root h, which I'm going to leave as calling it as h to the 1/2, a simple rearrangement, we can see that root h must be 4 minus u. So now it's a case of just transforming this into a form we can now integrate. So therefore, the integral of dh all over 4 minus root h, we can of course now just transform an awful lot into what we have here. So that's going to give us, as our first step, we're going to have -2h to the 1/2 du on the top, because that is what dh is. So we've got -2 h to the 1/2 du, just switching dh for what dh is in terms of du. And then the 4 minus root h, well, root h, of course, is 4 minus u. So the bottom is going to become 4 minus u, which again we can simplify now. So 4 minus 4 will obviously cancel, which is no bad thing. And so if we just rewrite this now, I'm going to have on the top -2 h to the 1/2 du, and on the bottom 4 minus 4, as I say, cancels, and minus u, of course, will become plus u. So now I'm trying to integrate with respect to u. That's in terms of u. This h to the 1/2 isn't. So the h to the 1/2 I can rearrange, I can replace with 4 minus u. So that's what we're going to do next. -2 and brackets 4 minus u. I'll just partition this off on the other side because I've got this in the way. There we go. So that's what h to the 1/2 is, all over u with respect to u. So after all this sort of fussing around, hopefully you can see now this isn't going to be so bad if I expand and simplify. So I'm going to get -8 on the top, then -2 times minus u is going to be positive 2u, so add 2u to both sides, all over u with respect to u. So now I'm pretty much ready to integrate this. So what's going to happen here is 2u divided by u, of course, will just become 2. In fact, I'm not sure I put this here. I'm going to neaten it up first. So I'm going to get 2u over u, which just becomes 2, and then -8 over u. All integrated with respect to u. So now, if I were to actually integrate this, what I'd get is the following. So I'm going to get 2u, because that constant 2 will integrate, of course, to 2u. 8 over u will integrate to, sorry, minus 8 over u will integrate to minus 8 ln of u. Ln, I should say, mod u. Plus, of course, some constant of integration. Now it's just a case of actually filling in what u actually was. So u, of course, is 4 minus root h. So we can sub this in. So now I'm going to have 2 lots of 4 minus root h. So that's going to give the next line 4 minus root h. I'm now going to put it back in terms of what the question's telling us, because we've done the awkward integration step now. Then minus 8 ln of the mod of 4 minus root h plus, of course, c. So it's almost in the right form, but as you can see, not quite. So what I'm going to do here, I'm going to just reorganize it so it's closer to the target. The target has minus 8 ln 4 minus root h first. I'm going to write this first. So minus 8 ln mod 4 minus root h, like so. And then over here, if I expand this out, I'm going to get minus 2 root h, because 2 times minus root h, and get minus 2 root h. 4 times 2, of course, is going to be 8, plus this c. So now, this k is just another constant. C, of course, is a constant. Any constant plus another constant will equal a constant. So 8 plus c is the same as a new constant, k. And that's my final step. So now I just say, this must be the same as 8 lots of a natural log of 4 minus root h minus 2 root h, and 8 plus c is the same as that k. And then we've done for part A of 14. 14b, we need to find now, according to this model, the range of heights of the trees in this particular species. And the range of heights can be modelled by this differential equation here. So, of course, the trees will be growing, which is dh by dt, and this is the formula for the growth. So what we can do here, we can assume the tree is always going to be growing until obviously they stop growing. So this value will be at least 0. So the range in heights of the trees, because this is at least 0, the time, of course, because we're starting from the time at 0, then what we can see is that this 4 minus root h must be greater than 0, because obviously we can't have a negative growth. We're not trying to think about the trees shrinking. We're thinking a bit too above and beyond there. So what we can think of here is that 4 minus root h must be greater than 0 to enable dh by dt to be non-negative. So if I just add root h to both sides, basically you can see that root h needs to be less than or equal to 4. So therefore, h needs to be less than 16 meters. So therefore, the range of heights of trees, if I just call this h, obviously no tree is going to be 0, but it could be a small sapling, so something bigger than 0, but it can't be any greater than 16. (14c), one of these trees was 1 meter high when it was first planted. So according to the model for part C, we need to calculate the time this tree would take to reach a height of 12 meters, giving our answer correct to 3 significant figures. I've just screenshotted here some of the key results we'll need to help answer this part C of the question. So we're going to start here. dh by dt equals this expression. what we need to do here is to separate the variables. And so from this, what we're going to end up with is the following. So if I just were to take this here and just plonk here what this is. So basically, if I divide both sides by 4 minus root h, that's going to give me dh all over 4 minus root h. And at the same time, if I multiply both sides by dt, then on the other side, I'm going to get t to the 0.25, still over that 20, with respect to time. I now integrate both sides. And so I integrate this side, and it will be equal to this, plus or minus some constant of integration. So that is our first step. Without knowing to do that, we'd be stuck before we can even begin. However, we can now use what we did from part A to help us. So on the left-hand side of this, I have this expression here, but part A told us it becomes this. Now, because I'm integrating, and this time we're going to actually find an exact height, I don't need to actually worry yet about this constant of integration here. I'm going to put this at the end. So going to be a constant of integration this side and a constant here on this side. I'll just rearrange it into just one constant at the end. So what I'm going to do from here now, if I rewrite this integral as this result, so minus 8 ln mod 4 minus root h minus 2 root h. So I've just rewrote that over here. Now on the other side, this one isn't actually so bad to integrate. This is just essentially just t to the quarter integrated. So this is going to be over here. I'll take the 1/20th to the outside. And now if I just increase the power of this by 1 to 1.25 and divide by that new power, I'm going to get 1 over 1.25 times t to the 1.25 plus some constant of integration. But now what we can do is actually work out what this constant of integration is. We're told one of these trees was 1 meter high when it was first planted. So from this, this is essentially telling us, without telling us, to sub in the value that when time is 0, the height is 1. When it was first planted, from the first second, it was 1 meter when it went into the ground. So from the off, when we start the stopwatch, the height was 1 meter. So we can sub this in. So now let's just do that. So now we just sub h equals 1 and t equals 0. So our next step is going to give the following. So this is going to become now minus 8 ln now this is going to become 4 minus root 1. So I'm just going to fill in what this is actually. So I'll just say it's 4 minus 1 minus 2 times root 1, which is just minus 2, of course. That'll give on the other side basically 1/20th times 1 over 1.25. Now when times 0, that's going to give times nothing essentially. So that's going to be times 0 plus c. So essentially all this bit here, because that's going to cancel, we know what c is. So essentially c is going to be that, because all this here is going to be 0. So therefore we can work out that our value of this constant c C is just going to be minus 8 ln of 3, because 4 minus 1 is 3, minus another 2. So we can now fill this in for the full model. So what we now have is, as a complete model, we're going to have that minus 8 over here, minus, whoops, let's start again with this. Yeah, lost my lines there a second. So now I know that C is that, I can now complete this model and see what we have. So I've got minus 8 ln mod 4 minus root h minus 2 lots of root h. That'll equal this thing here. Now, 1 over 20 times 1 over 1.25. I can simplify this into one fraction. That's just going to become 1/25. So that's going to give me 1 over 25 times t to the 1.25, sorry, plus c, which of course is minus 8 ln 3 minus ln, so just minus 2. So now what I need to do is to work out the time when the tree would reach a height of 12 meters. So what I need to do now is to rearrange this equation to get the time as the subject. So now, if I were to add on to both sides of this equation 8 ln 3 and 2, so plus 8 ln 3 and plus 2 to both sides, we'll get the following. So what I'm going to have now is that 1/25 of t to the 1.25 is going to be 8 ln 3 plus 2 minus 8 ln of 4 minus root h minus 2 lots of root h. So now I can rearrange this by first of all multiplying everything by 25 and then doing the 1.25 root. So therefore t is going to be the 1.25 root of 25 times all of this stuff. 8 ln 3 plus 2 minus 8 ln 4 minus root h minus 2 root h. Now I want to work out the time for the tree to reach 12 meters. So the final step now, I'm going to sub that h equals 12. So now if I sub in h equals 12, and then the required time that'll take will be 25 8 ln 3 plus 2 minus 8 ln of 4 minus root 12 minus 2 lots of root 12. And all of that is to the 1.25 root. So as long as we're careful when typing this in and subbing it in, we should be okay. So shift 1.25 root, that's going to be 25 lots of all of this. So it's going to be 8 ln 3, close brackets, plus 2, minus 8 lots of a natural log of 4 minus root 12, then minus 2 lots of root h. So minus 2 lots of the square root of 12. Press equals, and we get syntax error, which isn't very useful. So why have we gone wrong? I don't think I've finished off closing my last bracket, have I? That's it. So I need to close that last bracket, like so. And I then get a figure of 75.15-ish years. Which I'm going to round to 1 decimal place. I'm going to call that 75.2 years. That is a slow-growing tree. That's an awful long time, 75 years. So, that's all the questions done, then the whole paper. So I hope you found that useful. Thank you for joining along and listening, and I'll see you soon, hopefully, for paper 2. So keep working away, let me know if there's any problems, and best of luck in your final exams. For Mr. Bailey, it's goodbye.